this big thing called Skein theory. And there's a recent project I worked on defining a certain non-invariant we call the quantum A-polynomial. And I'm going to use that as sort of the motivating example that we're building up towards how does that construction work. I try to write my lectures to be 50 minutes long, so we have time for questions, and we won't miss lunch, even with questions. So do feel free to ask. And how I want to start off today in lecture 1 is I just want to talk about what are diagram magics and what are skeins. So this basic construction, and then later in the week we'll start moving later and later into the title. Okay, so the basic idea behind Skein theory is I want to use these graphs to model morphisms. And what I mean by that is I want to make some category. I'll call it, now this is not really a standard way of calling it, of graphs. And they're going to be colored by some other linear category. K, and I want a functor here. And I want this functor to send some graph like this to some morphism. Yeah, that looks too much like to some morphism. And the correspondence that we get to is we have some questions we need to ask ourselves about these graphs. We want to say what graphs are considered. So by this I mean, can they have, can they be trivalent or not? Or so what are they? What's being considered? Where do they live? So this is mainly a question of 2D or 3D, although here there's also questions of whether it's on a plane or on a sphere. And then also what extra structures do they have? So this is basically a question of, are they oriented? Are they framed? Basically this. And we'll see there's going to be a nice correspondence between these really graphical questions and what structures and properties C has. So what I want to do now is sort of make the idea of this correspondence precise, sort of by allowing myself to do more and more with my graphs, and as I do that, having more and more in my category. Okay. So I always start building up. So what if I just have my graph like this as a vertex, and what I want to do is I want to have colors, which means I pick my category C, and on the vertices I can put objects of C, so V and W, and sorry, on the edges I can have objects, and here at my vertex I'm going to make it big enough I can write some morphism. So F is some morphism from V to W like this. Okay, so I can do that. And this is fine. I'm not asking a lot from my category. But already a little thing that we see is we see some composition look like this. C, W, U. Right, you can picture a graph. And now I'm just only allowing 2-valent vertices. And this should be, what I'll see is I want this to be equivalent to something that's sort of G, like this. Okay, but from a graph theory perspective, this is super restrictive. So the next thing I want to do is I want to say, what if I have multiple or no strands? What does that look like? So say I have my F, and I have coming out of it 2 things, and I may be going into it as one thing, like this. So this could be v1, v2, and here there's some w. Or I would have something like this, maybe f, and there's some u going into it, and there's just nothing coming out. Yeah?
Is your convention top to bottom or bottom?
I will do from bottom to top. Yeah, thank you. But that convention does vary. All right, so what do I need here? Well, what I need on a categorical perspective is some canonical way of taking two objects in my category and putting them together and having a new object in my category. So I need that. So what this requires, and actually there's really gorgeous Hagoromo chalk, so let's use some colors. So here, what I see I need is I need a product. So I need something that goes from C tensor to C to C. My categories, I'm going to have them all be linear, so this will be some tensor product. And here, I need some canonical non-object, right? Something that if I can always put it next to another strand and it doesn't affect anything, so I also need what we call a unit, which I like to denote by blackboard bold 1. And altogether, what this gets me is I need a monoidal category. So this will now be C, it has some tensor product, and it has a unit, like this. And there will be some axioms that I won't go into to make this behave well. Okay. So multipolar no strands. This is already, we can model some stuff. What about if I have orientation? On my strands. We often like oriented graphs. So I have some strand V here. And I want to say I have the same thing colored, but in the opposite orientation. What's going on here? I have some object in my category, and I want some canonical associated object, right? And the way that this naturally turns out is we want duals in my category. So if I have some V, maybe I want some V star, like this. And how do I transition nicely into the formal axioms? Yeah, okay. And so we're going to make this exact. Considering two different graphs, we're going to be considering this one and this one, and I'll be considering them with either orientation. So this is going to be this way and this way, this way and this way, like this. And why would I consider these graphs for making this exact? Well, if you want duals in your category, the way that you do this naturally is you have some way of taking your original object and associating it with the dual object and going to the identity morphism. So I want one in this direction. I want one B in this direction, and I want the other way too. So from the unit to V tensor V, unit to V tensor V. And actually, let me double check I got the left and right duals correct. So it's very easy to get wrong. Yeah, I did in fact get the duals wrong. Like this. And you can see if I want this one to be V, going up and going down to be V dual. So this one's the V dual one. What these morphisms right here are giving for me is exactly that. So now I have a morphism from V to V dual to the unit. Right? So if I want orientation and I want to make it precise on the level of category, this is the type of graph that I consider. And here we have a very nice kind of correspondence topologically is on the level of graphs, we have isotopies. Right? So if I take a graph and I go like this, it's just isotopic to mass movement, right? These two lines are isotopic. And it's the same way to isotopic to going the other way. And this will be regardless of the orientation. So maybe I can draw it up. It would be the same one that's going down. And this is G-1 form symmetry. No, I'm kidding, I'm kidding. And we'll see that these axioms, what they're going to do is they're going to translate directly into sort of categorical demands on these morphisms here. So let's name these morphisms. So this is evaluation going this way. This is evaluation going this way. This one will be co-evaluation going this way. This is co-evaluation going the other way. And we can see that if I take this and I want to write down what would be the corresponding morphisms that I need, what am I going to get? So let's do that. Let's think what's happening down here. Sorry, I have to move boards. So here I have the identity. It's just a straight line, and I have this one, which is a co-evaluation. And it's co-evaluation going this way. And if I look above at the second part, I'll have evaluation and the identity in the other order. So this is evaluation. These are identity, and here it's vertical. And I have that this has to be equal to the identity. Here's this middle one. And then I could have, on the other graph, the same sort of working out goes like this, identity. Evaluation, and still, everything is this way. Okay, so if I want to have these graphs and I want to have the modeling categorical phenomenon, this is the sort of behavior that I need. And altogether what I get is I need C to be rigid, which is just the math term for having V for every object of V and V dual. And these evaluation and co-evaluation. Okay. Are we happy with this? Are there questions? All right. So now we have oriented graphs. A question asked, yeah.
So the co-evaluation, the arrow of the direction, does it go opposite or with the arrow of the diagonal?
If it goes opposite, it's because I did by accident. The opposite. I want it to do the same.
Okay, so it should match the arrow on the diagram. Ah, okay.
Did I draw it wrong though? It's super likely I did it wrong.
I think co-evaluation is.
Should I change it?
So in the evaluation, the right figure should be pointing up, so it should be presented.
Okay.
Okay. Thank you very much.
And also, like the lower, the blue color, the star V dual should be the right one, right?
Should it be? I thought in co-evaluation.
Both times you have like identity to V star tensor V.
Yeah, here it's V star here, and here's this V star here. Right?
I think this is correct now.
Yeah. Yeah.
How do you, I mean, but in the graph you just have the line going down, right?
Yeah. So this is a really good question. I'll repeat also for everyone online. The thing that was pointed out is that actually, when you start writing down dualities from a categorical perspective, you end up with a left and a right dual. But graphically, we don't distinguish between these. And this is, we'll see immediately, one of the first things that you demand of your category is that, yeah, these things aren't really distinguished. And the way that this, one way that this comes up is if you ask yourself, what about circles? I think this is the source of a lot of good math questions. So let's say I had a graph and I had a circle here. And here maybe we'll also figure out what nonsense I did with misevaluating things. And I want to be able to evaluate this, right? So this morphism down here and this morphism up here need to be able to compose. So let's figure out what this one was. So this is from here. It's going to be V Google, insert V. So this one is going to be going from the identity to that. And up here, I actually have the other V. So I have the other dual. Insert V. And I'm going up like this up to the unit. But you see, these are not the same, right? So in general, I wouldn't be able to compose these. So this is only also going to work if I have some canonical identification. V star isomorphic to V star in the other way. So we very quickly start to demand that our left and right dual are the same. And the existence of this morphism means we want C to be pivotal. Which is everything I've said before, plus the existence of this, and some nice compatibility stuff.
Sorry,
Yeah.
why do you ask that they're isomorphic? Couldn't you just have a morphism from one to the other?
If you want to agree with the math literature on like what evaluation and co-evaluation are, you end up having two left. Oh, you said equal.
I mean, you could replace that isomorphism with just any morphism and evaluate this, couldn't you?
Yeah. I've never seen someone work through that theory, so I don't know what would go wrong. So that could lead to something cool, but it's not what.
Okay.
Yeah. It's a good question. Other questions?
Are you always in this strict setting?
Yeah. For this talk, we're gonna be strict.
Sorry, could you again explain why you need like right and left duals?
So yeah, I think the reason. Does anyone know? I don't know an example off the top of my head where a category where they're different, but in general, in categories, there are examples of categories where they're different.
Mm-hmm.
I don't know about one because in Skein theory we always work with
If you have
categories.
an organism, I think will have algebra in many cases. Rep H will have duals given by S and the antipode, and they will not coincide, so it will be different left and right.
Even in a semi-simple case, if you have fermions or you have odd lines, then you have trouble identifying left and right duals. You run into a sign problem, and the fix for that is to put spin structures on circles and on lines. And if you track that, then you can fix it. But yes, that's can map.
Thank you to my co-organizers.
The associators come trivially from.
Yeah, we're not going to be talking about associators. Okay. We've built up a lot. I think it would be a good point to do a recap of where we've gotten. Maybe we've reached what you could call a checkpoint. So we have oriented planar graphs. Colored by a pivotal category. Right? That's what we were drawing here. And here we can think of these as forming some category, which we'll just call planar. Let's see. And what I've been going through sort of in a lackadaisical way is that we have some functor from this category to just back to C. So we have an evaluation functor. So I'll call this evaluation. Okay, so there's something we haven't talked about yet in our little list. So we've talked about oriented, we've talked about what graphs we consider. Now what I want to talk about is what if we want those graphs to be in 3 dimensions instead of just planar? What do we need? So if we want graphs in 3D, well, what can appear, which hasn't appeared so far, what this introduces is crossings. So something like this. So say this is living in a low cylinder like this, I can have V and W oriented like that. So I have some crossing, right? And what I want my evaluation map to sort of like, and I'm building up here, what I want is for that to be isotopy invariant. So let's say that this gets sent to some morphism C. I'll subscript it like this, from V tensor W to W tensor C. And I want to see just, if I ask that these graphs are up to isotopy, I'm going to get a lot of constraints on this morphism here. So what do I see? Is one thing that I see is if I have two curves like this, oriented up, right? This is isotopic to just two straight up curves like that. And what is this going to imply on this C? Well, it means that there's some other morphism that I can compose it with to get the identity. So this is going to mean C, little c, is invertible. Like this. Like that. And the other one that I'm going to get is, well, if I take, maybe I should draw this bigger. I have one curve here, and then here, let's just draw a box. And let's say I have some complicated graph, so gamma, some angle, like this. Well, this is going to be isomorphic to the same thing, but gamma happens after the crossing. Like that. So these two are isomorphic. And what is this going to demand? Well, this is going to turn into C is in fact a natural transformation. Right? Means it has some nice neutrality properties in both the front and the back strand. And I can get either from this or just from looking at another isotopy. I also have the following particularly important special case of this, which is if I take this beautiful tangle here, it's just drawing orientations, but downward orientation too. This is going to be isotopic to the same two front strands, with the back strand going on along the other side, like this. Right? You see this very back strand I've just moved from one side to the other. And what this means for me is that C is what's called a braiding. And altogether what I get from just wanting graphs in 3D is I get that C, the category, is what's called a ribbon category. Which means that it's braided, just meaning I have such this well-behaved isomorphism, and it's still pivotal, and that these two are compatible. All right, so I have this. And what I want to say is so far, everything our graphs have asked us for, every sort of isotope they've asked for, we've just said, yes, graph, you can do that. Now I want to give an example of something you might want from a graph perspective that we don't allow them to do. So another isotopy that you see often, I'll say this is framing, is that may also want this curve here, this is isotopic to this one. Okay. But this is too restrictive. Just from a cultural standpoint, there are categories C, we'll see some examples, that we want to study that wouldn't be compatible with this. So we don't ask for this. So we don't ask for this. Right? So we need some structure on our graphs that mean these are not the same. And what that means is I work with framed graphs. And this framing, one way I will never draw this again because it takes much longer to draw it, is we can think of all of our graphs as actually thickened like this. So you can think of them as thickened in some way. And you can think of that thickening as something that can be twisted around like that. Okay. And we don't call this is not the same as just the untwisted one. Okay, so this we don't demand. So this is just an isotopy. Now that I've gone through this, let's make some formal definitions. See what we've been building up to. So here's the definition of the category that I've been talking about. So let rib sub C category. So I want its objects to be make sure I say all the same words. There's some different notations. So oriented, C-labeled, or C-colored, zero manifolds in a disk. So for example, what I'll do is I could do something like this, oriented framed. And these can all be colored by objects in C, and it will have an orientation, plus or minus. So just for example, something like this. They'll be framed, but I'm not drawing the framing, because if we start drawing framings, we never stop drawing them. And so these are my objects, and my morphisms are going to be these oriented, framed, C-colored graphs. Now let's give these things a name. Their name is going to be ribbon graphs. Ribbon, just because we can draw them to look like ribbons that we've embedded. Okay, so an example of a morphism. I've drawn a bunch of examples, but sort of I can have some coupon, I can have some braiding, So this is the category that we're working with. And this idea of wanting to use this category to be able to draw pictures of our morphisms, I think one of the key components in the story is the following theorem, maybe the start of the story in some ways. This is from Rashtigan and Turaev in 9B, although there's also a very nice textbook on it, which is just by Tribe in 2001. So this is a textbook that talks about this. And here's the theorem. Let C be a ribbon category. There's a unique functor from rib C to C. I'll call it RT sub C in honor of these folks. So it's a unique functor such that, well, I'm going to require a couple of things. So I want, if I have a single coupon like this, I want that just to be sent to the coupon, right? I want that. So this is a requirement on the morphisms, right? I want RT C of plus V. I guess this is being implied here. I just want this to be V, and I want RT C minus V sent to be dual. So I want those, and I want it to be to respect the braiding integral structure, sort of the monoidal structure. So there's only, but once I require all these things, which are very reasonable to require, then I really just have one functor I need to worry about. Other questions?
Sorry, what kind of graphs are you talking about that like this framing issue is like too restrictive?
Oh, yeah, so the
I
problem
mean,
is...
like normally graphs are like vertices and like edges kind of, and then this should be like just the same, right? So like this seems to be an issue by like embedding graphs into like L3 or?
Yeah, this is like when I'm talking about three-dimensional graphs. And
You have like different embeddings that are like, and then this isotropy is like an identity between the two embeddings.
Yeah, so what can go wrong is here when I was talking about pivotal things, one way of talking about pivotality is I have an isomorphism from something to its double dual.
Okay.
And requiring this to be equality just means this has to be an equality.
Sorry, what does this mean on the graph level again?
So this means that this and this, so these two graphs are isotopic. But they're not if I put a framing on them, and here I'm thinking of like blackboard framing.
Okay, but like how do you think of these as graphs? I mean, like where are the vertices, where are like the edges?
Oh yeah, sorry, yeah. So
Two vertices, one edge, or?
yeah. So this would be the top and the bottom.
And like it's as graphs, they are the same, or?
Yeah, I mean, yeah. I guess I should say, I'm saying the word graphs because I like it, but yeah, you should
Like
really.
you're assuming more structure than like just a normal graph. So I'm wondering.
Yeah, I'm thinking of it with an embedding here.
The embedding.
Yeah, like an embedded graph. People say the word tangle also. I saw another hand. So
Yes. What is the definition of a ribbon category outside of like what we have been discussing?
wait, when did they show up?
Yeah, like I don't understand what's an example of this. Well, that's
Yeah. So we'll see.
that's not the graphs that we've been discussing.
Yeah. So that's there's a good point put in here. He's saying that if I just take rib, this is going to be a ribbon category. Very nice. But the general examples are going to be things like rep QG. Another way people like to write this is rep UQG, like this. So it's like representations of quantum groups, half algebras, stuff like that you should think of. Yeah, you can also symmetric monoidal categories are often ribbon.
Is this functor like a natural equivalence, or is that too strong?
It's not a natural equivalence, and that will be super important. Yeah, or a categorical equivalence. Yeah. So, all right. So the question actually that was just perfect that was asked is this an equivalence? And it turns out, no, it's not an equivalence. I don't want to erase that. I want to erase this. And in fact, some things are going to be identified by this graph which are not isotopic. So this is here. Now we're going to jump into doing some proper Skein theory. So here's my definition. And this is of Skein relations. So something I haven't talked about so far because it's not such a topological fact. I'm going to allow myself here to take finite sums of graphs. So I will allow myself to have things like this plus this. There's some morphism here. So we're going to allow finite sums because we will want to talk about linear categories. So 2.
Sum means composition.
No, it's like a formal sum.
Okay.
Yeah, it's not a topological operation. So 2 finite sums of C on the Rubin graphs are going to be, I'll say, just Skein equivalent. And I'll draw that as, I have some sum, and here I'll have some Ti morphisms I maybe from 0 to n. This would be equivalent to some other sum, T prime I goes from 0 to n. So this will be Skein equivalent if and only if Rashtig and Tarayev of these graphs, this thing, are actually equal. This. Like that. So I will say that they're equivalent if they're the same after evaluation. And let's do some examples of this. So here's an example which holds for every category. Well, in general, if I'm just thinking about isotopies, this thing that I drew earlier, where I had G and F one above the other, this and G, like this. These are not going to be the same tangle, right? One of these has 2 different vertices, one has the other vertice. So these are not actually the same tangle, but they are going to be Skein equivalent. And they are equivalent because they are both sent to by RT, so just F of G, and that agrees, right? So that's something that you would want to be equivalent, and our category would get unwieldy if it wasn't. So here's one example. Here's another sort of housekeeping example that you may want is V and W next to each other. I'm going to stop drawing the cylinder now. This and this are not. This is not the same. Not the same ribbon graphs, right? One has 2 strands, the other one has 1 strand, but they both get sent to. One gets sent to the identity. So I guess maybe this and this gets sent to this, maybe like this. And these are the same morphism, right? So these are going to be also Skein equivalent. Okay. Here is another example. If we take category C, the rep Q SL to C. So if you don't like, you haven't thought a lot about quantum groups before. What's going on here is I'm taking the symmetric monoidal category, just with representations of SL2C, and then I do some deformation, so it's not symmetric monoidal, it's just braided. So that's what this Q is doing for me. Then I get a really important relation, which looks like this. This thing, if I color by V, which is the fundamental representation, so this two-dimensional representation, this is going to be equivalent to, let me get the Q powers correct. Q plus Q inverse, like this, like that. So I'll get that, and then I'll also get, if I just have a single loop, let me get the orientation correct. Still followed by V. This is going to be equivalent to just, I have no loop, but I have a factor of, draw the factor first, minus Q squared plus Q minus squared, with just no loop, like that. And if you've seen Skein theory before, electron Skein theory, maybe they started off by just drawing these things. And that's because these were sort of the first set of Skein relations are studied in huge detail. It's one of the early ones. And these are called Kaufman, the Kaufman bracket. Skein relations. I just want to say, for some people, when they say Skein theory, they mean you look at graphs and you put this relation on them without thinking about ribbon categories in general.
Sorry, this is only true for fundamental representation or?
Yeah. But you use some nice, yeah, so the question was, this is a fundamental representation thing, but a special property of this category is that you can access all the irreducible representations, just considering the fundamental, which is a beautiful story.
Sorry, basic question. Is that supposed to be an equality or an isomorphism?
Okay. So now what I want to do is we make a series of jumps of where our graphs can live, and now we'll make, I think, kind of the most really cool inspired jump. And in doing so, what we'll do is we'll consider what are called Skein categories. And so the idea behind this is, what if we have our ribbon graphs in arbitrary three manifolds? How would we model this? Instead of just having them in R3 or in some thickened disk, I just want them in some three manifold. And so here's the idea, and how are we going to go about it? We're going to use this category of ribbon graphs, C, modded out by these Skein relations, as a sort of local model. And I won't talk about it during these lectures so explicitly, but if you want to take out the scare coats on this local model, what you'd have to use is something like factorization homology. Just if you hate square quotes, you know what that is. Okay. So here's our definition. So that's sigma be a surface. It can have boundary. It doesn't have to be closed. see a ribbon category. What I want to define is I want to define what I'll call Skein cat sub C of sigma. Like that. And so let me start actually with what the morphisms are. The morphisms are going to be C ribbon graphs in sigma cross 0, 1. So they'll, let's say, sigma is an annulus here. All right, so I can thicken it, and I'll try drawing my Skein solid yellow. Like this. So my morphisms can be something like this. They can interact with the topology. They, of course, can still have coupons. They're still oriented and colored, you know, however we like. So these are all colored, B, W, B times W, whatever. Yeah, they're all still colored. And so I'll have these ribbon graphs, but I want my Skein relations to come into it. So these are up to Skein relations in any embedded cylinder. So I want it in any embedded cylinder such that I know how to evaluate. So I can take the cylinder such that this, let's call this black variable D plus 0, 1, such that if I take my whole ribbon graph and I restrict it to this embedded cylinder, I can understand it as a morphism in rib C. So what does this look like? This looks like, well, if I take a cylinder and I can embed it like this, you know, I can have it come out like that. Like that. Now I have some understanding of Skein relations, right? This cylinder. And this whole business with wanting it to still be a morphism means, well, I don't want my graph to meet the sides of my cylinder, just the top and bottom. Okay. So these are my morphisms. What are my objects? So my objects are going to be these C-labeled, what I'll call C-labelings of sigma. So they're all going to look like sigma with a bunch of marked colored oriented points. This, so maybe plus, this one would be maybe plus V as an example. Okay, so now I have my Skein category. I've given you a definition. Let's talk about some properties of this.
So what do you mean by C labeling?
Yeah, so this is, I guess, I'm also defining this right now. Yeah, so C labeling of sigma is oriented, framed, C colored, 0 sub manifold of sigma. So it's just, if I look at one of these tangles and I restrict it to just the top and the bottom, what sort of object do I get? So an example would be just one point labeled by V.
So like this zero-dimensional submanifolds are points, but you're also like considering the tangles? Or
yeah, so the tangles are the morphisms. The tangles are the morphisms and the points are the objects. Yeah. And I'm saying zero manifolds because I don't want infinitely many points or something. I want finitely many points.
Mm-hmm. Yeah. So does all of this data, like for different two manifolds, assemble into like a 3D TQFT valued in?
Absolutely. Yeah, absolutely. Okay, let's get into some properties of this stuff. So here's some properties, and that will be the last property that I say today, I think. So one property is that if I look at the Skein category sigma of just the disk, right? This is really by construction just C again. So if I just plug the disk in and I do all this stuff, I've just described the disk again. So here's that's a nice property. If I look at Skein cat C itself, and I let this be free, like I just can plug in any surface, this is actually going to be a two-functor from a category surf to a category cat. Okay, so here this is going to be the category whose objects are surfaces. They can have boundaries, they can be open. One morphisms are, so I guess these are oriented surfaces. Morphisms are oriented embeddings. And two morphisms are isotopies of those embeddings. And then this one here is small k-linear categories with k-linear functors and natural transformations. Okay, so that's this two category, and this is this two category.
Sorry?
Yeah?
Why is the first one not a RIP C?
Because I take the quotient.
Ah.
Yeah. Because, and it's exactly because this is rib C quotiented by this thing.
Okay.
Yeah. Yeah, and that's how the proof, the proof goes. See this? Okay, more questions? I'll make the board taller.
It seems like the second property is independent of C.
The what?
Like, I don't see how the morphism between surface and one category is dependent.
So I get a different functor for every C. Yeah. And the way that C will show up is it's what's assigned to the disk.
So you said that the first thing is the categorical plane?
This?
Yes.
Yeah,
The first.
Yeah, this is a two category. And this is a two functor.
But the first one is just usual.
Yeah, because this is a category which is an object in a two category of one categories. Yeah. Yeah. And so these are nice properties of it. Let me say
Thank you.
I'm hungry. I think we're all hungry. Let me talk about Skein modules. And this is where we'll end. So here, for me, when we talk about a Skein module, what I want is I think about a free cobordism. I'll say sigma 0, m sigma 1. This is an oriented cobordism, so this means I just have some three manifold and identification of its boundary like this. So this is, I'm reducing the orientation. So I have this. Then what I can do is I get definition, the Skein bimodule. I'll call this SK underline M. And this is going to be, again, a functor from Skein category sigma 0. You may really want it to be from sigma 0 to sigma 1 Skein categories, but it's not. It goes like this. Sorry, this is sub sigma, or sub C, sigma cat, sub C, sigma 1, up, left. And what does it do? Well, here I will have some configuration of points. Say this is like an annulus. Some configuration of points like this. I call this x. And we can say this is the other nice to draw surface. Some disk with points. And what it's going to do is it's going to send these to the vector space spanned by we got so let's say, so here at the bottom, I need to show that in with some free morphism. Let's say the free morphism just caps this up, right? Or the coordism is just like this. And what it sends it to is the span of all these graphs, of all Rubin graphs in here. Maybe this right now. So this is the. So that notes this is the span of Rubin graphs. Rubin graphs in M with endpoints x and y, and this is up to Skein relations. And so here we had x, here we had y. When we give this thing a name, this is the final thing I do. This thing I will just call SKM xy. I'll call it the relative Skein module. Okay. I think as we started a little late, I will. I'll just say one more thing, and then we'll go, I promise. So I have this construction. I won't prove it, but this is a categorified 3D TQFT. And what this gives me is if I take this functor m and I evaluate it at the empty on both, so I just don't put any points here, right? This I get an action on one side of the endomorphisms of the empty for sigma 1, right? So by here I mean the Skein category with coefficients in C of sigma 1, and on the other way I get endomorphisms for sigma 0. This is just coming from it being a functor, right? So what I end up with is an actual, so I get a bimodule. Module here, and what I'm going to do is I'm going to call this the Skein module of M, coefficients in C, and these I will call the Skein algebras. Coefficients in C, sigma 1, and the same for that. So I get like an honest bimodule out of this construction in this way. But I think I'll stop there.
Make sure I'm understanding this. This makes it a 3D TQFT valued in like the Merida category of Ripon categories or something like this?
Yeah, it's valued in bimod, which is like two categories whose objects are linear categories, and whose one morphisms are functors like this, which are called profunctors sometimes. Yeah. But there's a Merida category.